In this session, we will be discussing about manipulator Jacobian. So what is a Jacobian? So Jacobian is a matrix that relates the joint velocities, which we represent as say q dot, and end effector velocities that let us represent it as x dot. Okay. So Jacobian, it is a matrix which relates these two variables, that is joint velocities and end effector velocity. So mathematically, you can write it as x dot is equal to j times q dot, right? So x dot, so it is a vector, and it has both linear velocity components and angular velocity components. So the Jacobian, the x dot, it will be represented at x dot is equal to say x dot y dot z dot. If it is a x y z represents the linear velocity components x y z, and alpha dot, beta dot, gamma dot. This represents the angular velocity components, right? So this is for a spatial form. So this vector representation of x dot, it is in for a spatial robot. So if it is a spatial robot, the size of the vector, it will be 6 cross 1. So that is equal to J. That is the Jacobian matrix. So let us represent it as in the generalized form. Say J11, J12, etc. up to J1n. And in the same way here, so it is J61, J62, etc. up to J6n. So the size of this Jacobian matrix, it would be 6 cross n. And then q dot. So q dot, it is the joint velocity. So it depends upon the number of joints in the particular manipulator. So the size of this vector, it will be also depending upon the number of joints. Say if you have n joints in the manipulator, so the size will be n cross 1, right? So this is the mathematical representation of Jacobian matrix. So x dot is equal to j times q dot, where x dot represents the um, uh, velocity components with both angular and linear velocity, and q dot refers to the joint velocities. Clear? And coming to the Jacobian matrix, the columns of the Jacobian matrix, they are associated with the robot joints. So each column, it will represent the effect of the end effector velocities due to the variation in each joint velocity. That is the first column. If we take the first column, it will represent the effect of the joint 1 velocity, that is q1 dot, on the end effector velocity x, capital X dot. Okay. So what is the effect on the first joint velocity on the end effector velocity? That is related by the first column of the Jacobian matrix, right? So the size in the generalized form, as you see, the size of the Jacobian matrix, it depends upon the number of joints. So here we have taken n as the number of joints. So see the size of the Jacobian matrix, it will be 6 cross n. Having learned that what is Jacobian, now we should also know how to analyze a Jacobian matrix. So with an example, we will just learn how to analyze a Jacobian matrix. Now consider a 6R manipulator. So 6R manipulator, so it has 6 joints and all are revolute joints. So the configuration, so in a particular configuration of the manipulator, we are going to analyze the Jacobian. So let us say the configuration of the manipulator or the joint configuration as q1 pi by 2, q2 equal to 0, q3 minus pi by 2, and q4, q5, q6 are equal to 0. So for in this particular joint configuration, the Jacobian matrix that we have obtained is J is equal to this matrix. This is the size of the matrix. It is 6 cross 6. As you have 6 joints, so it is 6 cross n. So a 6 cross 6, right? So now let us analyze this Jacobian matrix. So let us first consider the first row. Okay, so consider this first row and the sixth row here, right? So from these two rows, you can just get the equations as so x dot is equal to, remember the Jacobian, it relates the end effector velocities with the joint velocities. So we can write it as x dot is equal to minus 70 times q1 dot. So that is the equation that we get from the first row. Now from the sixth row, we get that omega z dot, that is angular velocity related to the z axis, that is equal to q1 dot, because you have one at the places here. Q1, Q2 is 0, Q3 is 0, Q4 here, that is Q4 dot, Q5 dot is 0, Q6 dot. So the equation becomes Q1 dot plus Q4 dot plus Q6 dot. This analysis is important because in kinematic control, we need to move the robot in specific direction. So the Jacobian will tell us which joint can be used, right? So with the Jacobian, so from this, using these equations, we can infer that which joint can be used for moving the robot in specific directions. Similarly, when we observe the joints 2, 3 and 5, right? So when we just observe the joints 2, 3 and 5, they contribute to the linear velocity in y coordinate and the angular velocity in the x coordinate. It is more easy to see that the linear velocity component is more sensitive to the variations of joint 2 compared to the variations of joint 3. So a rotation in Q2, it will implies a higher linear displacement of the end effector compared to the same rotation in Q3, right? And if you just check the rank of this Jacobian matrix, when you just check the rank of the Jacobian matrix, it is equal to 4. So which means that no matter what values we provide to the joint velocities, the linear velocities in the z direction as well as the angular velocity in the y coordinate cannot be instantly modified in this configuration. As because the rank is reduced, certain components of the velocities cannot be modified. So that is by analyzing the Jacobian matrix, we can say that whatever values we provide to the joint velocities, the linear velocity in the z direction. So as because this complete row here, it is full 0, right? So this is the one which is reducing the rank of the matrix. The Jacobian is not in full rank. So if it is in full rank, then you should get the Jacobian rank to be 6. But you find that the rank of the Jacobian, it is not equal to 6 and it is equal to 4. It is because that you have two rows that is completely 0 here, right? So if at all your rank is reduced, so here from this Jacobian, we can say that though you provide the joint velocities, the linear velocity in the z direction. So this row, it relates the linear velocity in the z direction as well as the angular velocity in the y coordinate. So this row is responsible for the angular velocity in the y coordinate. So this cannot be modified instantly in this particular configuration, right? This is because that the rank is reduced by 2 and there are two directions that are not allowed in many cases. So this is how we will analyze the Jacobian matrix. In the next following sessions, we'll be discussing about how to derive the Jacobian of manipulators. With few examples, we will be discussing.